the last thing, the last two things, I guess, they are related to each other that we're going to do. So remember equilibrium, right? We have where we could have the forward reaction and we could have the reverse reaction. And I put the regular arrow here because the computer doesn't always let me put in the equilibrium arrow. But when we have a chemical reaction with equilibrium, then we can create this expression for the equilibrium constant. Okay, so KEQ is called the equilibrium constant, where when we solve, do you guys remember that the brackets stand for molarity? So when it says like A in brackets, that means molarity, okay? And it's the product over the reactant when we said that. So for the reaction, where A plus B are both reactants and C and D are both products, the products on top, the reactants on bottom. Now, before, I know it's been a lot in the crash course and all this stuff, but before when we did like the rate equals K times this in brackets to the X, remember that? That's been a while since the beginning of the week. We did not include the coefficient. Okay, but now with the KEQ, you do include the coefficient. So the lowercase letters are the coefficients, and how you include them is those become the exponents or the powers, whatever they are. So it really only matters if it's not a 1 for a coefficient, then you plug it in, okay? So this is just a ratio. We're actually going to solve for the number for KEQ. That's why I said we need a calculator today. And it helps us to see whether there's more products or more reactants at equilibrium, okay? And so, like I said, the brackets are the concentrations in molarity, moles divided by liters. And because of this, we only include gaseous and aqueous particles. We don't have to include solids and liquids. Those are excluded, just like we did before. So we never include solids and liquids, okay? And the value depends on temperature. So for KEQ, it all depends on the temperature of the reaction, but we're not going to include that. You just need to know that if the temperature changes, then the K would change. And it's really nice because there's no label, there's no unit needed for the KEQ because everything just cancels everything out, which is awesome. Okay, so no label required for that. So we'll solve for it in a second, but when we look at the actual number for the KEQ, the equilibrium constant, it tells us whether reactants or products are more favored. So if it's a very large value, like times 10 to the positive exponent, then that tells us that it has mainly products present. And that's because of the product over reactant dividing. The bigger number would be the numerator. Okay. So it's products when it's a big number. It's reactants when it's a small number. So like times 10 to the negative 11. It's a very, very tiny number. So that means that it contains mostly reactants because the reactants would be in the denominator. So when you divide, the denominator would be bigger to make it a small number. Okay. Now, if it's like right around 1, then we say that's kind of like a medium value. Okay. And that just means that you have both reactant and product significantly in there. So it's almost like they're almost equal amount of reactants and products overall. So you might get a question where it asks you at equilibrium, which is more favored, reactants or products? And so you just need to know what is the big number is products, when the small number is reactants, and that's all you got to get, right? So we're going to do example 4, where we're going to write the expression, and then we're going to plug in the numbers and solve, okay? So the reaction we're talking about here is between the dinitrogen tetroxide, which is the N2O4, and nitrogen originally, I think I gave you a balanced equation, but I forgot here. So it's always just good to check to make sure the equation is balanced because the coefficients matter now. And if this is not a balanced equation, so what should we do to balance it?
Put a 2 on the NO2.
Right here? Okay. Sounds familiar. We did that before in our lifetime this year. Long time ago. Okay. So this is our reaction. And we want to write the expression, so like product over reactant. And then we also want to calculate for the value of the constant. So we want to calculate for the K. Okay. Now I do not have very much space, so I need to add a slide. Okay, so for our KEQ, it's always product over reactant. Okay, so right side over left side. All right. So on the right side, we have that NO2. They're both gases, so they both get included. So it's going to be in brackets the concentration of NO2. And we put a coefficient on the NO2. So that means that 2 coefficient means that we're going to square that. Okay. And then that's the only product we have. So then on the bottom, we put the reactant, which was in brackets, the N2O4. And that one did not have a coefficient, so it's just going to be like that. Okay. So this is 1 out of the 2 points, is just writing this. So on any of these problems, first thing you should do is write out the expression. Okay, when it says expression, that's what it means. Okay. Then when you want to calculate the constant value, we plug numbers in. Okay. Now this is where I got tricky. Okay. You see where it says a liter? And it's like 1 liter, right? And then we've got moles. And we've got moles. Gotta be careful about what those moles are about. Does anybody remember how we get, so if the brackets mean molarity, does anybody remember what we do to find molarity? Like what is it really divided? It's gonna be moles and liters. Is moles on top divided by liters, or is the liters on top divided by moles? Moles are on top. So to find the concentration, to find the molarity, the equation we had from chapter 16 was that the moles are divided by the liters. Okay. Now, I'm saying this just because, like, I'm not going to trick you. Okay. But since technically the numbers are in moles, that means that we should take the moles amount divided by the liters amount. But since it's just a liter, 1 liter, that means that the numbers are just the numbers. Okay. So I hope I don't trick anybody, but you should just plug the numbers in. Okay. So in our equation, we're going to be careful and plug the NO2, the 0.030 on top, because NO2 we put on top, and then the 0.0045 on the bottom, because that's where we put the N2O4. Okay. So to find the KEQ, we're going to put that 0.030, fill it in for the NO2 spot, and don't forget the square, so we're going to have to square that number, divided by the N2O4, which was 0.0045. Okay. Now, it's just all we have to do is solve. So when we are solving, we have to make sure that we square it before we divide. Okay, so how I would type this in my calculator is I do the 0.03, then hit the square button, and then that answer is divided by 0.0045. You guys see on your calculators where the square button is?
Anybody need help finding that? Okay, my calculator up.
On mine, it has like the X to the 2. So if you don't know where your square button is, I can help you find that. But what do you get? What's the answer? 0.2? Okay. Now, if you didn't get 0.2, it's probably just typing it in the calculator wrong. I can help you with that. Okay. But the 2 things. 1, no label, no unit. Okay, that's great. That's okay. Second, though, we do need a round of significant figures. So for the 2 numbers, they're all tricky because all these zeros, right? But both of these numbers are the same amount of significant figures. How many sig figs? 2. The 3 0 pounds and the 4 5 pounds. So both of them are 2. Now, is the 0.2 currently 2 significant figures? No, it's not. Because the 0 before, remember all the zeros before don't count. So how do I make it 2? Add another 0 at the end. So 0.20 would be the correct way to round to 2 significant figures. Okay. So we're getting places, but we're not done yet. So this example that we just did, example 4, is like what you're going to do in the packet, reactions and equilibrium. It's like number 5 and number 6. Okay. So we're going to keep going in the notes, but if we want to do one of those together, we can. Maybe number 5 will be together. But I wanted to continue with the notes so that we just get it done. Get it over. Okay. Any questions? All right. So the last thing that we have is actually really related to what we just did. Okay. The difference is that we're talking about with solubility equilibria is that when we dissolve solids into water to make aqueous solutions, sometimes they're really soluble and sometimes they're not. We had it in chapter 11. We had what are called the solubility rules. They're on the back of your new periodic table, where we like said that anytime it includes a nitrate, always aqueous, or like we have soluble and insoluble as the word. So we oftentimes will generalize about the compounds that are this slightly soluble type, that we just say that they're insoluble. But in reality, they do dissolve to some extent. Okay. And that's why on the terms, on the tables, on the notes, on the rules, they're always labeled as slightly soluble. Because technically a little tiny bit of them does dissolve, but just a significant amount does not. That's why it's referred to as slightly soluble. Okay. So to compare the solubility when you dissolve a solid into a liquid, water. Okay. The AB solid would be like the solid compound at the beginning. And then the right side, like the A and the B, these are the ions that were made to write the formula AB. Okay. And then we do have to balance it still, just like we have to balance all of our equations. But when we are trying to find the equilibrium for the solubility of this solid, then we have this KSP. So KSP stands for solubility product, and it is the product of the 2 aqueous ions that are formed when it dissolves. Because remember, this whole time we haven't been including solids or liquids. So when you write the expression, you never look at the left side. You only look at the right side. So it's very similar to what we just did. And the coefficients become the charge, and the brackets mean concentration. Okay. Now, a lot of the time, we're going to know what the KSP is. Okay. And we're going to have to solve for the rest. So that is going to take a little bit of work, but I'll tell you what to do. So it's also good to know before I move on, because I forgot about the first part. That the smaller the number of the KSP, the smallly. So it's going to be less likely to dissolve if you have a really, really small number. Okay. So this table is given. Now, for every problem, I'm going to tell you what the KSP is because there's tons and tons of numbers here, right? So whatever compound we're talking about, I'll just give you what it is. But looking at the numbers, like if we look at like the aluminum hydroxide, that KSP value is 1.26 times 10 to the negative 33rd. That's extremely small. Okay. Versus like the lithium carbonate right next door to it is 1.7 times 10 to the negative 2. That is significantly larger than 10 to the negative 30. Okay. So that just shows us that the aluminum hydroxide will probably not dissolve hardly at all, but the lithium carbonate could dissolve a lot better. Okay. So when we're solving these problems, you're going to be given a chemical. On the worksheet, on the packet, I was very nice, and I actually gave you the formula of the chemical. I just didn't do it again, because I'm going to so you're going to have to make sure that you have the correct formula. Okay. And then if you're solving for concentration, so this one we want to solve for concentration. Whenever you're solving for concentration, you replace the concentration with X. So we're just gonna solve for X for things that we don't know. Okay. And it has to be multiplied by the coefficient. So I don't know if we have that here, so we might need to do one from the packet so that we know what I mean when I say multiply by the coefficient. Okay. So first thing though, let's just write out the KSP. Let's figure out what lead carbonate is first of all. Before I'm getting ahead of myself. Okay. So we want to know the concentration of the lead ions, chromate ions, when they dissolve in an aqueous solution for lead chromate. So first thing we need to know is what the formula of lead chromate. Does anybody remember what that Roman numeral means? It's the charge. Yes, the charge, the power, the charge. Does anybody remember what the symbol of lead is? ED, thumbs up. Yep, okay. So now, I'm going to show you how you can do this like that, okay? So if I know that the PD, that is PD plus 2, right? So on the left side, that's going to be the solid where everything's written together. On the product side, that's going to be the ions that are separate. So I know that the PD plus 2 is part of this. So I'm just going to go ahead and write that on the product side. Then once I figure out what chromate is, I know what to do for the left side. Okay. We'll see how that's a little bit different when I give you the formula. But okay, so PD plus 2 is the cation. Now the chromate is the anion. And now we haven't done this in a very long time, like 12 or something. ATP ending tells us that it is a polyatomic ion, which is on the back side of your new periodic table. So does somebody have that out? Can you tell me what chromate is? CrO4 negative 2. Okay. So that's one of those ones where it has lots of them together, right? So the other thing on the product side, so like the anion, will be the CrO4 negative 2. Okay. Now technically we got to finish this equation. So to do the solid on the right side or on the left side, in my directions and stuff, we are just going to combine these two ions to make it into one. Now, this has been a while, but the charges are plus 2 minus 2. Those just cancel each other out, right? So the formula for lead chromate is just going to be PbCrO4 because there's the positive and the negative are able to cancel each other out already. We don't have to do that whole like process thing, which is great. Okay, so now that we have our equation, it's already balanced, right? Yeah. Okay, so that's important because we are not going to have anything because our coefficients are 1, which is great. Okay. So now, for our expression for the KFT, we don't include the solid. The solid is just there to make sure we balance it correctly. Okay. But we're just going to include the 2 ions. So it's going to be the EV plus 2 in brackets for the concentration. And we don't need a charge because it is a coefficient 1 times the concentration of the CrO4 minus 2. Now, at this point, if you forget to put the plus 2 and the minus 2 in the bracket, I'm not going to count. Okay. So if you just forget to write those down, it's okay. Also, you don't necessarily have to put the ACS as long as you know that you're going to use them. That's fine. Okay. So now, what we're going to solve, we want to actually know what the PD plus 2 bracket, the concentration is, and we want to know what the CrO4 negative 2 concentration is. Okay. We are given the KFT number. So that gets plugged in to the left, the KFT. So KFT is 1.8 times 10 to the negative 14. And then this is where I said when we solve for concentration, we replace it with X. So everywhere that you have brackets, we're just going to replace with X. Because that's what we're trying to find. Okay? So since we have PD plus 2 and CrO4 both in brackets, we're going to put an X for the PD plus 2. And we're going to put an X times an X for the CrO4 negative 2. So, and the reason why we do that and plug the same number in is because the coefficients are both 1. So that means that when we get the answer, the concentrations for both of them are going to be the same number because it's a 1-to-1 ratio. Okay. So now, to simplify, we got 1.8 times 10 to the negative 14, and that's really X squared, right? So how are we going to get X by itself? Take a square root. Yep, you thought you were done with math. Okay, we'll start out with math today. Sorry. So square root to get rid of the square. Okay. Now, on my calculators, if you got like a fancier calculator than mine, you get to hit the square root button first and then type the number in. On mine, sorry, I blanked it. On my calculators, if you're using mine, you have to type the number in first and then hit the square root button. So just it's a different way to type it in. But either way, you should get the same answer. And it's going to probably be like a bunch of zeros. It's going to be really small, right? So let's put that in scientific notation. We don't have to write those zeros out. I wrote down that the answer is 1.3 times 10 to the negative 7. So if you get it on your calculator and you like count over all those zeros, it should be 7 spaces to make it be 1.3. 3, 4. Okay. Oh, sorry. I just did 6 things already because the 1.8 just makes it be 2 6 6. So, and then when it's brackets, it has a unit this time. Concentration. What's our unit for concentration? What is concentration really? It's molarity. So we're going to put an M for the label. How do you have a question? Yeah, so what I did is I put 1.8 double E negative 14 and then hit the square root button. Did you get it? Okay. Yeah. So this is the answer. Now, that is it for chapter 18 notes. Okay. Let's do some problems in the homework packet together so then you just don't have to do it yourself. Does that sound like a good plan? Yes. Sounds like one. So please help us. Because it's Friday and we're tired of this.